Hello everyone. So welcome to the video series of XCAN, and in this video we will be learning about Arbitrum precompiles, and we will code like how you can connect with Arbitrum precompile and you can retrieve an information from Arbitrum precompile. We will walk you through what is the meaning of precompile, how it is different from the normal smart contracts, where the precompiles are being stored, and what is the difference between normal smart contract calling and the precompile calling. So we will walk you through all of that thing. So let's jump into it. As you can see, this is the eighth module, which is named as precompile playground. Here you will master Arbitrum's precompile through interactive coding challenges. So as of now, we have added 6 challenges into it, and we are looking forward to add more challenges into it so that you can gain more understanding about Arbitrum's precompiles. So in this module, you will learn about interactive coding challenges, some gas optimizations, and about Arbitrum precompiles. So first, let me give you a brief overview of what is the meaning of Arbitrum precompiles. Yeah. So what are precompiles? So precompiles are special built-in smart contracts which are stored at particular fixed addresses, and it is executed natively by the blockchain client itself instead of through the EVM bytecode. So what happens is when you compile any smart contract which is written in Solidity language, you will get two things. First is contract ABI and second is contracts bytecode. Now, EVM means Ethereum Virtual Machine will execute the EVM bytecode, and each bytecode will have certain operations, and for each operations it will have opcodes, and opcodes will different opcodes will cost you different gas. As you can see, these are the opcodes. If you want to do addition, multiplication, subtraction, or division of any two numbers, then these are the opcodes, and for all these opcodes different gas cost will be there. Okay, so this will be there in the Arbitrum bytecode level, and EVM will execute it at the on-chain level. And but uh, in the precompile, everything will be executed natively by the blockchain client itself, means at off-chain. Means they exist. Precompiles are exist to handle computationally expensive or protocol level operation like hashing, cryptography, or L1 to L2 bridging, because these things are very computationally expensive if stored on chain. So that's why this will kept at system level so that it saves gas cost. And the third point is when a transaction calls a precompile address, the EVM routes it directly to native code itself, means like ArbOS in Arbitrum. So in the Arbitrum, there is a configuration for all precompiles come from ArbOS, which is the native client of Arbitrum. And if we are using it, it will help us returning results faster with predefined gas costs. So if you are, as I said earlier, in normal smart contracts, if you are writing, then it will execute at bytecode level at EVM, and for each operation different opcode will be there which cost you a different gas cost. But as precompiles are already defined by the system and has been already configured at the client level, so all the gas costs are predefined. And unlike normal contract which has stored as on-chain bytecode, precompiles lives off-chain in the client software itself, and their addresses are also unique. Okay, and if you want to change the normal contract, then you have to redeploy the contract and you have to make upgrade the contract. And if you are redeploying the contract, then every time you are redeploying the contract, newer contract address will be generated. But as precompiles are not stored on chain, so if you want to change any functionality in the contract, then a ArbOS upgrade means system level upgrade will be required, because all contracts are already compiled ahead of time by Arbitrum native client itself, which is ArbOS. So if anything needs to be changed in the contract, then that can be only changed once ArbOS system level upgrade comes. And if in the normal cases, when you are working with a normal smart contracts, if you want to change anything, then you can update the contract and the contract addresses will change, but that won't be the case with precompiles. So there are some precompiles like ArbSys, ArbGasInfo, ArbRetriable transaction, which are given by Arbitrum native client ArbOS. Okay, so moving forward, as we have explained that precompiles or precompiled contract are special smart contracts that are built directly into a blockchain's protocol at the native client level rather than being deployed at regular contract bytecode level. Precompiles are written in blockchain's client's native language, such as Rust or Go or C++. Means native blockchain's client's native language means the language in which that blockchain's node are being written. For example, for Arbitrum, precompiles implementation are done in Go language rather than in the smart contract languages like Solidity. This makes it extremely faster and gas efficient. And as we have seen that their addresses are fixed like this 0x01, 0x02. And some expensive cryptographic and mathematical operation which is too expensive are done by effectively using precompiles. So these are some common precompile addresses for the Ethereum. Okay. So the difference between normal and regular smart contract is regular smart contracts are written in Solidity, stored on-chain, compiled to bytecode, which has been deployed to blockchain and stored on blockchain state and executed by EVM, where precompiles are written in blockchain client's native language. Means ArbOS is written in Go language, so that all precompiles will be written in Go language, and it's not stored on the on-chain, and it executed directly by the client, and it is much faster. And as we have seen that you can't redeploy the new precompile if you want to change it, because it requires a system level upgrade or hard fork where all nodes upgrade their client software to include the new precompile logic. Okay, so Arbitrum precompile has two components. First is the Go implementation and second one is Solidity interface. So Go implementation is one where actual logic of precompile is there, which is written in Go and lives on the Arbitrum Nitro client node, and it executes natively when called, just like Ethereum precompiles. This is what actually runs on the Arbitrum node, while the Solidity interface is it it only has interface, means a kind of method signature will only be there. It does not have contain the body, means it does not have actual implementation. It provides a developer friendly way to call the precompiles from Solidity. So it acts as a contract ABI that tells your Solidity contract how to interact with the precompiles. If you are importing ArbSys precompile, and if you are doing this in your contract, then what actually happens is your Solidity contract makes a call to this address 100, means 0x000 till 100, and Arbitrum Nitro client intercepts this call. Instead of looking at the bytecode level, it recognizes that this is the precompile address and it should be executed at client level. So Arbitrum Nitro will check this, and so the execution will actually done at the Go implementation, and the result will send back to the user. And if any state will be updated, then that will be made on chain, but the execution of this will be made off chain by via Go implementation via Nitro client. So Arbitrum Nitro's role is, so it is a Arbitrum blockchain client, just like Geth is for Ethereum. So it is the software that runs Arbitrum nodes, processes the transaction, executes the Arbitrum virtual machine, contains all the precompiled implementation in Go language, and returns back the executed result to the user who have called this precompiles function. So just like normal smart contract, you can call the functions of precompiles, and these are the some addresses where the precompiles, and why both exist is Go code is where the actual implementation is there for the efficient implementation, and Solidity interface is developer kind of convenience that lets you call all precompiles using Solidity language. Okay, so in regular smart contract, what happens is once you are calling it, it read the bytecode from the blockchain state, execute the bytecodes in virtual machine, and it will gives you the result, which all this happening in on chain. And what at precompile, what happens is it recognizes that the address which user has called is a special like this 0x64. So it identifies that this is a precompiled address so that it executes the native Go function from the client software, and the result will be sent back to the user who have called the function from the Arbitrum precompile. So no bytecode exists at this address at blockchain states. When called, Nitro recognizes that this is the precompiled address, and instead of reading data from blockchain, it runs Go code compiled into the Nitro binary. And the code exists in the node software at ArbOS, not in the blockchain data. So the key difference is on the regular contract, data is stored on blockchain. Here, data is stored on nodes software. Okay. And if you want to deploy a new version, it requires a protocol update, and anyone can verify the bytecode. And here you must trust the blockchain client who is managing the software. Still, the data is on chain because for the precompiled code doesn't live on chain, it lives off chain, but the execution and state changes is still part of the on-chain transaction. So why precompiled cost less gas? Because in the regular smart contracts, everything happens on-chain at EVM bytecode level, and it have opcodes which sometimes contains some expression of high gas cost. But in precompile, everything runs as native compile code and direct execution handled by CPU. So gas cost is low. In normal smart contract, execution complexity might there in VM opcodes, which might be expensive. Here everything is fixed and predefined and precompiled, so execution is cheap. So why this design? As I already told that some system level things and mathematical and cryptographical things might be very expensive. So if we include them in precompile, then it might help us for the cheaper execution. Okay, so that is all for the precompile. Now let's move towards the eighth module, which is precompile playground. Click on start learning. You will be redirected to this page where as of now we have 6 challenges. Once you are completing all of these 6 challenges, you will able to mint your NFT certificate for the eighth module. You can also filter out the challenges based on the difficulties like this, based on the categories, and based on the precompiles which is being used in the challenges. Let me walk you through the UI of it. For example, we want to do the second challenge, block number check. So as you can see, it is showing that ArbSys precompile is used in this challenge, which is a system level precompiles. Okay, so these all are the precompiles which are available, and these all precompiles are provided by ArbOS. So as you can see, these are all are the precompiles like ArbGasInfo, which gives you information about gas pricing. System level functionalities information are provided by ArbSys precompile. If you want to cache your contract, then these two precompiles are used, which is ArbWasm and ArbWasm cache, which we also have seen in the caching in Arbitrum stylus video. Okay, so these all are the precompiles where as we have seen that the interface will be Solidity and the actual implementation will be there in Go language, and this code will be executed by Arbitrum client level itself. So don't deep dive into the actual implementation because it might get very overwhelming and bit difficult, as we don't need to understand about each and every precompile mentioned here. We only need to understand about 3 to 4 precompiles, which are ArbGasInfo, ArbSys, ArbWasm, and ArbWasm cache. So only these 3 to 4 precompiles are at our use cases. So I will let you walk throughout all these precompiles. So yeah, moving forward. So let's look at this block number check challenge. Difficulty and everything has been mentioned here. These all are the instructions, and here you will be able to see the hints if you stuck on the challenge. Click on the view hints and you will be able to see the challenge hits, and these are the test cases which you can run once you write your code. Okay, so you can also jump into another challenges using this sidebar. And yeah, so let's go through the instruction first. Retrieve the current Arbitrum block number. So we want to retrieve the latest Arbitrum block number on which the transaction has been made. So first let's open Sepolia RB Scan Explorer to check that which is the current latest block number is there. For example, 1 second ago, this is the latest block number 21204948 3. So if you are refreshing it, then you will get a newer block, because at each second so many blocks are being produced at the chain. So we need to retrieve this latest block on which the transaction has been added and on which the latest block has been mined. So as we have seen that for the system level retrieval, we can use ArbSys precompile, ArbSys for layer 2 specific system information. Here layer 2 is Arbitrum, and we want to fetch the information of latest block number from Arbitrum. So ArbSys precompile will be used. So we got one hint that ArbSys precompile will be used in this challenge. Okay. So in this challenge, you will learn how to access Arbitrum's current block number using ArbSys precompile. So your task is to create a function called getCurrentBlockNumber that connects to Arbitrum sys precompile on Arbitrum Sepolia first. Then it calls the appropriate method to get the current Arbitrum block number and returns the block number. So this is the JavaScript code which you need to write, and here are some notes. You have to use the ether.js library which has been already imported for you, as you can see here. And we have also given you the ArbSys precompile address, like where it is located. We have already added the precompile address so that you don't need to find it from the official Arbitrum docs. You can also find it from the docs that what is the address of it. It is 0x64, which is 0x64. And inside it, you have to look into the implementation of it, like which all functions are available, because we want to fetch the current block number. So you have to go through the whole code first, like which function can be used to get the block number. So yeah, as you can see that in the Solidity interface, it has the function name ArbBlockNumber, which returns the block number. Okay, but this is the interface, so this is only the function signature, and the actual implementation of it lies in the Go code for that function. For example, here is the ArbBlockNumber to get the current L2 block number. To get the current block number, the implementation of it lies in the Go code. So we have seen that this function will be used ArbBlockNumber to get the block number. Okay, so let me open the hints one by one so that we can get an idea. So the first hint is, what specific precompiles are you going to use? As we needs to fetch the system level information, means block number, so we need to use ArbSys precompile. Second hint is, remember define the correct ABI for the function you are trying to call. So this is the ABI. This is the ABI, means this is the function signature using which we will get the latest block number. And third hint is, to return the value the structure matters, make sure that you are returning exactly what the test expects. Means here we are expecting that we needs to return the block number so that it will be an integer. You can't return like this, return hello, because this is a string. So if you run this code, then you will get an error because it's not matched with what the code expects to return. Fourth hint is, if you are struggling with a specific function, try reading the Arbitrum documentation for the precompile. As we have already read the documentation, this function will be used, and that was the ABI for that function, means this is the function signature. And last hint is, double check your parameter types. Blockchain functions are very sensitive to exact data types. Means, for example, if this function expects to pass certain parameters, then you have to pass that parameters in the exact same order, right? But here we don't need to pass any parameter, as simply we want to extract the block number. So let's try to code this. So the first thing is, we have already identified that ArbSys precompile will be used, and we want to fetch the current block from the Arbitrum Sepolia. So to connect with Arbitrum Sepolia, we need to know the RPC URL of the Arbitrum Sepolia, right? Because we want to fetch the block number from Arbitrum Sepolia, so we need to first get address of it. Okay, so let me explain you what I have done here is, as you can see, first of all, we are connecting to Arbitrum Sepolia using this RPC URL for the Sepolia. So now we are connected to Arbitrum Sepolia. Then we have added this contract address because we want to call the function of our block number for this contract, right? So we have to pass the address at which chain, means at mainnet or at Sepolia. You want to fetch the block number of Sepolia or for the mainnet, but we want to fetch the block number for Sepolia testnet, so we have added Sepolia URL. Then we need to define the ABI, as we have already seen in some previous video that if we want to call any function from the smart contract, then we have to pass the exact signature of it, and that we got from here, right? So we have added the ABI, and now we are creating a contract instance where we have to pass the contract address, contract ABI, and the provider. Now what does it mean is, we wants to interact with the contract which has been located as this address which we have passed, and from this contract we wants to call this method of the function, this method of that contract, and that contract is deployed at Arbitrum Sepolia. So this lines means that thing. And once we got the that instance, then we can simply call this method arb block number, and we are storing that in the variable, and then we are returning that block number. Click on run tests, and yeah, as you can see that the challenge is completed because all test cases has been passed. And you can see, if you want to print the number, block number, then you can also print it. Current number is block number 52042, 52042, that is at here 52042. So because so many blocks are generated at each second and we have refreshed it, so it took around 1 to 2 seconds to refresh the page so that newer blocks came. So yeah, that's how you can retrieve the latest block. And we have submitted our solution. We have also seen the test cases. Here is the execution time and the estimated gas cost for the code which you have written. And yeah, that's how you have to write the code for all these 6 challenges. Yeah, so if you come at the playground button, we have integrated code compiler. If you want to test your code at here, then you can do it. You can write your JavaScript code here and then simply click on run code. Then your output will be printed here, hello from JavaScript. If you are coming from C++ or Rust background, you can simply switch to that and write your code here and test your code from this beautiful playground. Yeah, so that's all from this pre-compiled video. If you have any doubt, then please feel free to reach out to us. Thank you. Happy building.